Hello everyone and welcome to our calculus notes for section 4.1. Today we're talking about antiderivatives and indefinite integrals. So this is the start of the second major portion of calculus, and we're talking about integrals here. And so we're just going to start off with the concept of an antiderivative. So a lot of these questions you can answer on your own. You might want to go through these and just see if you can do them on your own. And if you get stuck, you can always refer to the video here. But I'll just walk you through these. So in example 1, it says find the derivative, then answer the question. So the derivative with respect to x of x squared, well, we know by the power rule is just 2x to the first. So the question, 2x is the derivative of what function? Okay, see how we word that? So 2x is the derivative of the x squared function. Now the definition of an antiderivative, here we have a capital F of x is an antiderivative of lowercase f if capital F prime of x equals f of x for all x in the domain. Okay, so what that means is if the derivative of this capital F function equals the lowercase f function, then we know that that capital F function is the antiderivative. Okay, so the question says find the antiderivative, capital F of x, of the function f of x equals 2x. So if we use our question, f of x is the derivative of what function? Okay, so we could reword that and say 2x is the derivative of what function? And we would say that is x squared from right up here. So if capital F of x is a function, how many outputs should there be for each input? This is just a basic question about functions. So for every input, there's going to be one output. Okay, and that was just our definition of a function. There's one output for each. In example 2, we're asked to determine the following derivatives. And if we look at our functions here, we have x squared plus 1, x squared minus 2, and x squared plus 2. So let's go ahead and find these derivatives using the power rule. So here we would have f1 prime of x equals 2x. And then for letter B, we would have f2 prime of x equals, well, 2x. Because the constant here, the derivative of the constant is 0. And here, f3 prime of x would equal 2x. And again, plus 0 because of our constant. So, does adding a constant to our function, f of x, change the derivative? Well, no, it doesn't. Describe what adding a constant does to your function. Well, here we have the graphs. Here is x squared. Here would be x squared plus 1. Here's x squared plus 3. Here's x squared minus 2. So adding these constants, all it does is shift this function up or down. You can see here that it's exactly the same graph except it's been shifted. So the constant shifts f of x vertically. And that's all it does. So how does each function relate to the derivative of 2x? The slopes are going to be the same. And each has a derivative of 2x. So if we just went like at x equals 1 and we were to draw the slope here, on all these graphs, you can see that they're all going to be the same. So what does this mean for our antiderivatives? So here was the derivative of 2x. So the antiderivative could have been x squared plus 1, right? Because it gave a derivative of 2x. The antiderivative could have also been x squared minus 2. Could have been this example, because the derivative is 2x. Could have also been x squared plus 2 from this example. This graph right here, notice the slope is still going to be the same, so x squared plus 3 would work. Really, any x squared plus any constant could be an antiderivative of 2x. So we're going to talk about a general solution of a differential equation now, f of x. And we're going to call it capital G of x, and the G, of course, stands for general solution. So capital G of x is just going to be capital F of x plus c. So instead of writing all of these other antiderivatives right here, we're actually just going to write a general answer for the antiderivative. So here's our f of x equals 2x. So our capital F of x, remember, was x squared. And so our g of x, or our general solution, is going to be x squared plus some constant c. So anytime you find that antiderivative, it's going to be very important to give the general solution of the plus c. All right, so now we're going to talk about something called indefinite integration. And we've already dealt a little bit with the antiderivative, and we're going to rename this, and it's also going to be called the indefinite integral. And it's the solution to a differential equation. And so the process of antidifferentiation is going to be called indefinite integration. And those are the same things. And this is the process of finding all solutions to a differential equation. And we think that integration is the inverse of differentiation. So as we were differentiating, notice the symbols here. Capital F went to lowercase f, went to f prime, went to f double prime, f triple prime, so on and so forth. So differentiating is the process of going in this direction. Integrating then is going backwards, going the other direction. So if we had f triple prime of x and we integrated it, we would get f double prime. If we integrated f double prime, we would get f prime. If we integrated f prime, we would get f. And if we integrate f, we get capital F. So we can see this inverse sort of relationship there. So let's talk about the notation now of an antiderivative. Okay, and so we can say y equals the integral. So there's our integral sign. It's kind of looks like an S. And we're going to see how this actually relates to an S, or a sum, in the subsequent sections. But there's our integral sign. And then here's the integrand. And this is basically the derivative that we're trying to find the antiderivative of. The dx here is the variable of integration. So this is read as the antiderivative of f with respect to x, or the integral of f of x with respect to x. Now we're going to say that this equals capital F of x plus c, and that c is your constant of integration, and that's always just going to be plus c. So for example 4, we want to solve for y. We want to figure out what the integral of 2x cubed with respect to x. Okay, so basically we're going to have to think backwards. What function gave us this derivative? So if we remember, here is the general power rule for our here's the general power rule for derivatives. So if we had some function a times x to the n, recall what that derivative was. Remember the n multiplied the a and then subtracted 1. So when we see this, we know that we would get a times n times x to the n minus 1. Now, what we need to do in this case is realize that this is the derivative. Okay, so we have 2x cubed. We're going to set that equal to our power rule formula for the derivative. So this is the derivative, this is the derivative. And let's go ahead and start comparing parts here. So this 2 is equal to an. Okay, we can see that right there. And then this 3 up here is going to equal n minus 1. And then the x, of course, is just our variable, so we don't do anything with that. Now, if we look 2 equals an, we have two variables we can't solve. In this case, though, 3 equals n minus 1, we can actually solve for n. So we're going to add 1 to both sides. And we know that n has to equal 4. Now, we can use substitution over here and say, let's see, 2 equals a times 4. And so if we want to solve for a, we just divide by 4. And we get a equals 1/2. Okay, so how does that help us solve our problem here? Well, remember, this right here is your derivative, or y prime. And this here is our y. And the process of finding an antiderivative is going from this y prime to the y. And so we know the y prime here was anx to the n minus 1, which was 2x cubed. And what we did is we found out what a equaled and what n equaled. So now we just have to reapply this to ax to the n. Okay, and in this case we have a was 1/2, x was just x, and then n is 4. So the antiderivative or integral, indefinite integral of 2x cubed dx is 1/2 x to the 4th power. Okay, so we don't want to have to go through that process every single time of setting it equal to x to the n minus 1, and instead we're going to actually get a power rule for integration here. So if we see a derivative in this form, ax to the n, we can find its antiderivative by just following what we did here. So let's take a look and see. Let's equate these here. So from this 3 here, how did I get to this 4? Well, it looks like I added 1, and you can see that I added 1 right there. So that's 3 plus 1. Now that 2, how did I get it to be the 1/2? Well, it was right over here. I took 2 and I divided by the 4, which remember was the 3 plus 1. So this was really divided by the 3 plus 1. Okay. Now the 3, this is our n right here. So that's n plus 1. And we actually want to divide that 2 also by n plus 1. So let's formalize this now. Here is our ax to the n. So we know it's going to be ax to the n plus 1, so we have to add 1 to that exponent. And then we're actually divide this also by n plus 1. And that is the simple power rule for integration. Now a couple other integration properties that we get here. The integral of 0 dx. Remember, we have to go backwards, so we have to think what the derivative of what function gives us 0? Well, we know the derivative of a constant gives us 0. If we're looking at the derivative of, if we're looking at the integral of k dx, k is just some constant. Okay, so we think here we want to go backwards. So this is going to be kx plus c. So the integral of a constant is just going to be that constant times x, and then again plus c. In this case, the integral of a constant multiple, so it's k times f of x. What we can do with that constant is we can actually take that out and say it's k times the integral of f of x dx. Okay? And so that constant will really just get multiplied by the antiderivative, capital F of x, plus c. Okay, so that's how you can deal with constants that you find in your integral. Now, if we have the integral of two functions that are added or subtracted together, okay, we can actually separate these functions out. So this would be like the integral of f of x dx plus or minus the integral of g of x dx. So these are just some simple things that might help us find some antiderivatives. Now we want to do some practice finding indefinite integrals, and notice you can always check your answer by differentiation. And these first few examples are only going to use our general power rule. Okay, so this first one is the integral of 5x to the 7th with respect to x. Now here, let's use our general power rule. So you're going to get 5x to the 7 plus 1. We're not going to write this out every time, but just for this time. And then divided by that 7 plus 1. And so we can see here we're going to get 5x to the 8th over 8. Okay, so pretty simple. 7 plus 1 is 8, and then also divide it by that 8. Now, because this is just an antiderivative, notice this is just one possible answer. So we always have to make sure that we do our general form and put plus c. Now let's go ahead and check this by differentiation. So let's go ahead and find the derivative with respect to x of 5x to the 8th over 8. Okay, so we know we have to do 8 times 5, which is 40. And then we have to subtract the 1, so to the 7th, and then we still have that divided by 8. So 40 over 8 is 5x to the 7th. And you can check here that that was our original answer. So we know that this has to be the antiderivative because the derivative of it is the 5x to the 7th. All right, for our next one, the same tricks apply. If we have something like 4 over x squared, we want to rewrite that as 4x to the negative 2. So just bring that exponent up and make it negative. Now let's use our general power rule. Have to be careful with our negatives. So we still have our 4x, and let's add 1 to negative 2. Well, negative 2 plus 1, okay, and that's going to be over negative 2 plus 1. So when we add 1 to negative 2, we actually get negative 1. This will be over negative 1. All right, and if we were to rewrite this now, we would bring the x to the negative 1 back underneath, and we still have a negative 1. So we get negative 4 over x to the first. And what do we always have with an antiderivative? That plus c. Okay, let's go ahead and find the derivative here of negative 4 over x. Okay, so we know when it's on the bottom, it changes sign, so the negative changes to a positive, and then it actually increases by 1 here. So we do get 4 over x squared, which was our original, so it checks out. All right, in example 3, notice now we have four different terms here. And the different terms of polynomial function don't phase us. We do the same process for antidifferentiation. We use the power rule on each one. So for this first one, we're going to get 3x, and then negative 5 plus 1 is negative 4 over that negative 4. In our next one, we have minus 7x, and then 3 plus 1 is 4, and that's going to be over 4. Here we have minus x. So our exponent here is really a 1. So we need to do 1 plus 1 and get 2, and then divided by 2, and then plus 3. Well, when we think about 3, you can actually think of 3x to the 0 power. And so 0 plus 1 is actually 1. So it's x to the first, and then over 1, and it doesn't change. You could also remember, if you go back to this one right here, that the integral of a constant is a constant times x, which is what we have right here. So it's the 3 times the x. And we want to do that plus c because we're finding the antiderivative, and really the general solution has to have that plus c. Okay, so go ahead and find this derivative really quickly. So we would have negative 4 times 3 over the negative 4. So we have 3x, and then this has to decrease by 1, so negative 5. Here we have 4 times the 7, and then divided by 4, so it's really negative 7x. Decrease this by 1, goes to 3. Here, 2 times negative 1/2 is just negative 1. And then if we decrease the 2 by 1, we just have 1. The derivative of 3x is just 3. The derivative of a constant is 0. And you can see that it matches. And so this is the correct indefinite integral. All right, for example 4, nothing new here, but we do want to change this derivative, square root of x. We want to change it to x to the 1/2. So again, we don't like our radicals because they don't really help us out too much. Okay, so let's go ahead and find this using the power rule. So we still have the x, and we want to add 1 to 1/2. So now we're at 3/2, and then we want to divide by that 3/2. Now just to rewrite this so it's a little more pleasing, we actually are going to get 2x to the 3/2 over 3. Okay, and this is also plus c. Check your derivative. 3/2 times 2/3. Now that's just x, and then 3/2 minus 1 is just 1/2, which is the square root of x, which was our original problem. All right, for number 5, here we have a quotient, and unfortunately, with indefinite integration, we don't have anything like a quotient rule. So what we actually have to do is rewrite this. And so the first thing I'm going to do is write this as x plus 1 times x to the negative 1/2. Okay, any problems there? So this was x to the 1/2, but because it's in the denominator, we can move it to the numerator by changing the sign of the exponent. And what we actually want to do here is distribute this, okay, and multiply these factors together. So we actually have the indefinite integral of, let's see, this was x to the 1 times x to the negative 1/2. So that's just x to the 1/2. And then 1 times x to the negative 1/2 is just x to the negative 1/2 dx. Now here we have a function, two functions added together, so we just find the indefinite integral of each one and add them together. So for x to the 1/2, we already found that it was So x to the 1/2. So we add 1 here and divide by that same number. Now x to the negative 1/2, we want to add 1. So negative 1/2 plus 1 is 1/2. And divide by that number. And we have our plus c, of course. And then we'll just rewrite our fractions here. So 2x to the 3/2 over 3. And then in this one, we just are going to get 2x to the 1/2. And that's going to be plus c at the end. Okay, let's just check here. 3/2 times 2/3 is just x. And then minus here, so it's x to the 1/2. We can see that part. And here 1/2 times 2 is 1, x to the, well, 1/2 minus 1 is negative 1/2. And we see x to the negative 1/2 here. So we know we did the indefinite integration correctly. Now another tool we have, we can actually use division here. And so in this case, I want to actually separate your numerator and divide it by the denominator. And yes, this is okay. The only thing you can never separate is the denominator, but you can always separate out the numerator into 2 fractions here. Okay. Now you could have done the same process that we did before, gone x to the negative 2 and multiplied, or you can do it this way. So now, if we simplify this, x squared over x squared is just 1. And then 1 over x squared is x to the negative 2. Okay, so the integral, definite integral of a constant, is going to be that constant times x. So that's just x. And here, x to the negative 2, we're going to add 1 to that negative 2. So now we're at negative 1. And then we divide by that number, negative 1. And then plus c. And so here, let's rewrite this, x minus 1 over x. And then plus c. Okay. Now you could add these back together. Just change this into x squared over x. And so we really have x squared minus 1 over x plus c. All right, so that is an antiderivative and how to find an indefinite integral using the power rule.